This is about an ultra-wideband filter working from 800 megahertz, 80 megahertz to 6 gigahertz with 5 embedded high-rejection notched bands. And this has been designed and fabricated by RF Microtech, which is located in Perugia. So this is the outline of the presentation. I will first go to the motivation for this work, introduce the specs and the analysis of the specs, and then illustrate the design procedure and the optimization that we made using AWR. The filter was fabricated and the design was validated, and then some conclusion. So the reason for this work is connected to the EXPO in Milan, which started last May. This is the plan of the exposition, and there are several mobile service providers that use different base stations for coverage at this of this area. You can see that each base station covers a different area in the EXPO, and at the same time, the government has established one base station for security control, working up to 6 gigahertz in covering all EXPO areas. The problem arose because there are some secondary lobes of the antennas for the mobile service that interfere with the installation for security reasons, for security control. So in order to allow the mobile service station to coexist with this control service, we needed notched filters to prevent the interference phenomenon to take place. So notched filters can be used and should be used to avoid such interferences, and those were incorporated into the base station of the security control antenna to allow the coexistence of all systems. So in terms of specifications, our customer H3G asked for a 2-port device which would be able to provide high rejection notched bands at all mobile frequencies to allow the coexistence of the various systems. And the bands are indicated here. Okay, this is 800 megahertz, 900 megahertz, approximately 1.8 gigahertz, 2.1 gigahertz, 2.5 gigahertz approximately. And the rejection was required to be higher than 35 dBs. And there is some mistake here in the numbers. Yeah. And anyway, the overall bandwidth covered by the filter is almost 200%, exactly 195%. And the maximum insertion loss should be in the range between 2 and 3 dBs. So the dimensional constraints were not very stringent, but roughly 1 by 1 by 0.2 meters. The main problem was that the request came to us in the month of April, asking for the filter to be ready by the 1st of May. And of course we explained to them that it was not such an easy task to perform. But anyway, we asked for a delay of 15 days, and we were able to deliver the filter on the 11th of May. So this the mask illustrated the request from the customer. You see here the 5 bands over quite a large frequency band, and the rejection here must be minus 35 dBs. And so we needed to design 5 notched band filters that we identify with the number from 1 to 5. And here we see that the idea is to design 5 different filters to be connected along in a cascade along a low loss transmission line, TEM line, to connecting the various filters. So each filter is to be a nth order notch band filter consisting of the cascade of n, depending on the order of the filter, shunt resonators. And the first analysis revealed that the various orders should be between 4 and 5 resonators for each filter. The first two filters required only 4 resonators, while the others require 5 resonators. So for each resonator, we needed a very high unloaded Q, above 1000, and the main difficulty here, because of the very wide band, was to avoid the spurious modes up to 6 GHz, to avoid any response degradation. So how did we proceed? This is the schematic of the various steps. So the first step was to identify a circuit model using AWR. And this shows you the simplified circuit model. So we have the various resonators. This is one of the filters that is illustrated in this equivalent circuit. Transmission zeros are realized by shunt series resonators, which are separated by TM lines of lambda over 4 lengths at the center frequency of the filter. And losses are also included in the model through resistors that model the losses according to this simple formula. So this is an example of the response of this equivalent circuit using the AWR simulator. You see here the notched band here with well, theoretically, of course, you have a very high rejection in this band. The transition between the stop band and the pass band depends on the number of elements or the order of the filter and on the unloaded Q of the resonator. So the next step, after having identified the circuit model, is to go to the full wave design. So we have to identify a 3-dimensional structure capable to produce the same response or about the same response as the equivalent circuit model. So as transmission line, we decided to use a low loss TM line made of rectangular coaxial line. This is because, of course, this has the same behavior of a conventional coaxial line, but this is easier to manufacture, and you can also play with the dimensions in order to adapt your resonator depending on the geometrical constraint. So you see here different geometries that correspond to the same characteristic impedance of 50 ohm. So this picture shows you how the transmission line is an example of the transmission line. You see here the connector, the transition between N-type connector to rectangular transmission line, and all these transmission lines have the same impedance, but with different geometries. You can notice here that the center conductor must be held by support. We chose a plastic support of PTFE, and of course correspondingly we modify the geometry of the transmission line in order to maintain the same characteristic impedance. So the resonators were designed as a simple stub resonator, short circuit at one end, and coupled to the main line through a capacitance here. You can see the coupling capacitance, and this is the main 50 ohm transmission line. So for filters number 3, 4, and 5, we simply realized 3 shielded λ/4 resonators according to this simple geometry. And we can notice that the capacitance here determines both the resonance frequency of the resonator and also the coupling to the transmission line. We noticed, unfortunately, that a λ/4 resonator resonating at 1.8 gigahertz has the first higher resonance at 5.4 gigahertz, which is below 6 gigahertz. So this cannot be used because we don't want any spurious resonance up to 6 gigahertz. So in order to push to higher frequencies the second resonance, we modify the geometry by increasing the end capacitance of the resonator, and at the same time shortening the length of the resonator. This way, this geometry can have a higher frequency, which is above 6 gigahertz. So we can move up the second resonance of this resonator. So you see here the typical response of this resonator. And the full wave full wave response has been matched to in order to have the same response as the circuit model in AWR. And this shows you the complete geometry of the filter with the 5 resonators, and this is the corresponding circuit model in AWR. Of course, what is important is also the length of these transmission lines between adjacent resonators, which is approximately λ/4, but of course it's not exactly λ/4 because of the spurious reactances associated with the discontinuities. So for the filters number 1 and 2, which are the most critical ones, the ratio between F1 and for the first higher resonance and the first higher resonance and the dominant resonance is above 6. So this type of geometry could not be used. So we had to utilize a different geometry for the first 2 filters, which are the lowest frequencies. So in this case, we needed to increase the coupling capacitance between the resonator and the transmission line. So we ended up with a planar configuration. You see here the capacitance here, which is above the main transmission line, and this is the resonator. And this is the tuning screw because, as you can imagine, at the end we needed to do some tuning at the end after fabrication. So this is the geometry of the single resonator, which was used for the notch filters number 1 and number 2. And this type of geometry allowed us to have a very wide spurious-free resonator filter. And this is the typical geometry of the first 2 filters with 4 resonators of the type I've just described. The total length here is about 200 millimeters, so it's a relatively large filter because of the low frequency involved. Again, the transmission lines connected to the resonators are about λ/4. So what you see here is the comparison between the full wave model and the circuit model. You see that we have a quite good agreement. Of course, you cannot have a perfect agreement, but this is satisfactory in the sense that they both match the specifications. So this was the design procedure for each single filter. Then you have to connect the filters one to each other, and also to not only with connecting lines, but also taking into account the various discontinuities which are included in the I didn't go into details, but of course you have also to design the transition, the supporting blocks, the bands, etc. So all this must be taken into account. So in a few words, each notch band filter has been imported into AWR as a S2P file, and then of course we didn't have time to make an optimization using a Ful-wave model. So we decided to go to circuit optimization, which is of course much faster, and optimize the length between each block using circuit simulation. And of course, this is a quite critical phase of the design, because of course the transmission line lengths between the blocks are critical in determining the insertion loss and return loss, and so the performance of the whole filter in the entire band. And at the same time, we had no time to make several trials, so we had to be very quick, as I said. So transmission line lengths were modified according to optimization done on the overall filter for optimizing return loss and insertion loss using circuit optimization. More than 5 blocks were imported from the Ful-wave model, because as a Ful-wave modeling was done using HFSS, and the models were imported into AWR. This is the complete schematic that you see. The filter is a quite big structure with the 5 filters cascaded together with the bands and all discontinuities, etc., etc. So we add 17 touchstone blocks plus 16 transmission lines to be optimized in, as I said before. Okay, this is the optimizer response using AWR in this complete frequency band. And okay, if you and the last step was to perform a final full-wave analysis of the entire filter. After that, we went to the fabrication of the filter. This is a three-dimensional schematic of the filter. Input output, which you see here the first band notch band filter, second one, and 3, 5, and 4. We try to keep the structure of the filter as symmetric as possible, and you see here all the elements, blocks that constituted the filter. One entire full-wave simulation required 46 hours, so you can understand it was a bit critical in terms of time. So this is the final full-wave simulation, and the comparison between AWR optimized structure and the simulated three-dimensional full-wave simulation, which HFSS was considered to be satisfactory. And so the filter was fabricated and validated. This is the 3D representation sketch of the filter. Of course, nothing can work at the first time, so we needed some additional tuning, but the filter we had only one sample of the filter, so we had no much choice. And but we were quite lucky, if you like, and it worked. After some tuning, it worked in a satisfactory manner. This size here is about 70 centimeters, and 35 or so in the other direction. This small piece of aluminium is not essential part of the filter. It was just to resemble this the shape of the filter to a 3, which was the logo of our customer. So it was just a courtesy that we made to the customer. And so this is the measured, and well, you see the 3 responses: the circuit response according to AWR, the Ful-wave response according to HFSS, and the measurement that we made on the field. So we are quite nothing can be perfect, but at least the customer was very happy, and so also we were quite happy. So just a summary is that they required. By the way, not only the customer, also the Italian government came to check that the filter was behaving as they wanted. So, as I said, the device consists of several cascaded blocks, and the distance between the blocks was optimized in order to optimize the return loss and insertion loss. A design procedure based essentially on circuit model using AWR was effectively developed and applied. So the Ful-wave was used only at the end to check the overall behavior of the filter. So I think that AWR demonstrated the potentiality in matching the urgency that we had in performing and finalizing the project. And the final check by Ful-wave simulation experiments validated the design procedure. And this device, if you want, maybe you can ask and see it at the EXPO in Milan. Thank you very much for your attention.